Alright, good afternoon. Let's finish the poll placement and then we'll get on to another new topic, okay? Yeah. Maybe just a clarification on the calculator that I sent it out for the midterms. Okay, some of you have the latest model of that the TI calculator, right? Yeah, which I believe has file storage. I don't know how far it can go. So if you don't want to buy another calculator, you want to use that one, that's fine. But then you have to make sure you reset it to clear out the content. Okay, yeah. The only thing I wanted to prevent is people access internet or somehow store something in a calculator, right? So bottom line is, I know all of you guys, trust all of you guys, and don't think you wanted to risk anything at this stage, right? So that's very important, okay? Yeah, but otherwise, anything is fine in terms of calculator, okay? Yeah. Okay, so let's look at the poll placement, okay, and then let's continue on the poll placement. In previous lecture, I gave you a couple examples already in terms of how to do poll placement, okay, to control the system. So here's a quick summary or bigger picture. This is the original system, right? This is your system. Just create one here. You design a negative feedback control system by letting u equal to negative k times x over k. Okay. So all of this together, right? So with this negative feedback, you basically end up with the so-called regulator. Okay, or we call this the regulation problem. Okay, so regulation problem, as we explained, essentially what it means is you were given certain non-initial condition, right? And then we're designing this control parameter k such that the x of k will go back to 0. That's as simple as it is. That's basically what a regulator means. Okay? And later in this lecture, we'll look at the reference control. So this is not the tracking yet. Okay, this is basically, it's not asking you to design a controller to track certain type of reference input. This is essentially just design a controller such that you bring your system initial response back to 0. Okay, you can basically we consider the initial value here as some sort of a disturbance here. The simple negative feedback will give you a closed loop. Basically, will give you a closed loop, which is x of k plus 1 equal to g minus hk, then times x of k. So plugging this u back over here, and you'll get this closed loop response from the system here. The g minus hk essentially is the closed loop system matrix at here. So this is the closed loop system matrix, and we can easily derive. We can set this determinant to be 0. We can easily derive the so-called basically closed loop characteristic equation, right? So this is essentially will give us the closed loop characteristic equation, and expand it for this determinant. Okay, chances are it can be written as, depends on how many type of what types of eigenvectors this matrix has. But let's just say we have n number of distinct eigenvalues. Okay, so for this particular determinant, you can write it into a multiplication of different factors. Each one essentially contains that eigenvalues here. Okay, so lambda 1 up to lambda n. So they're the so-called desired. They're basically desired poles, right? of course, the desired where they're from. They're from a careful selection of this k value, the control gain k at here. And you can expand these factors, and you can end up with basically an order n polynomial. So expand it, you can end up with the order n polynomial here, right? The coefficients of the polynomial are definitely related to the value of the eigenvalues or desired pole set here. So this one here, we can call it the so-called desired closed loop characteristic equation. Okay. So this is important. This is general. You can order n here. If n is equal to 2 or 3, you can just simply shrink that to the appropriate order. Okay. So this is the bigger picture. Yeah. And I used a couple of very simple system order of n to illustrate how the capital K, this gain matrix K, can be calculated. Okay, based on a certain criteria, right? Yeah. Okay, so in this part of the lecture here, okay, and what we wanted to do, we wanted to come up with a little more general formula in terms of calculating the K at here. Okay, so I'll give you a couple of different methods here. The first method is basically for the solution of gain K. Okay, yeah. So, what can we use? The first kind of approach. So this first method here uses the so-called control canonical form. Okay. So if you recall, when we learned the steps for discretizing for obtaining a discrete state space model, the first step, of course, is always continuous system, and then you can, from the continuous system, you can derive the pulse trans function by considering a zero-order whole equivalent, right? And then from the pulse trans function, we can draw different type of simulation diagrams. There's one type of simulation diagram give us the so-called control canonical. There's another type will give us so-called the observable canonical, right? And there's another type can give us the so-called Jordan format. So this is basically from here. Let's consider the control canonical form. So let's say, for example, we have a pulse trans function. So I'm going to use the most general format at here. Okay, so we have, let's say, a pulse trans function in the format like this. Okay. So from here we can definitely draw certain type of simulation diagram to derive this discrete state space model, right? And one of the solution is the control canonical. So for control canonical, the matrix G, if you recall that, it's 0, 1, 0, 0 here, 0, 0, 1, and 0. Okay, and then keeps going here. Here's 0, 0, 0, and then here's 1, and the last row at here, okay, is negative an minus 1, negative a minus 2. Here is negative a1, and then h is 0, 0, to 0, 1 here. Right, that's control canonical. This is a part of the formula. You can put it into your formula sheet. Okay, yeah. So the idea essentially, okay, given a system, so any system, you can have infinite number of ways to put it into this state space model, right? There are infinite, basically, solutions for the state space equation. And one of them is this control canonical format. Okay. So the benefit of this control canonical format is, if we look at the system, this is system matrix G. If we look at the open loop, basically the original system's characteristic equation, right? That's how you do for characteristic equation. You use Zi minus G and let the determinant go to 0. And because the unique feature of this determinant here, a lot of zero terms here, right? There are a lot of zero terms, okay? A lot of zero terms. So when you calculate the determinant, and it turns out this determinant just simply to be Z to the power of n plus a1, okay, Z to the power n minus 1, and then an minus 1 Z plus an equal to 0. It's very, very simple. Okay, so a lot of these zero elements at here, and that give us a fairly straightforward characteristic equation, whose coefficient happen to be basically the coefficient for the denominator. Okay, yeah, you can try it yourself. I mean, this basically just plugging a unit matrix Z into all the diagonal elements here, and then the rest of them put a negative sign, right? And then taking determinant, you get this one here. Okay. So why this format will help us in terms of calculating the gain matrix thing, right? So let's think about it now. So now we see, okay, I wanted to obtain an appropriate gain matrix K. So let's let this gain matrix K equal to this vector here. Okay. So gain matrix K is always n 1 by n matrix, because you're going to use the K multiplied by the column vector X, right? So this is a 1 by n at here. Okay. Then plugging this K, into the negative feedback as I did it over here to obtain a closed loop, basically closed loop characteristic equation. So you get a G minus HK, right? Okay. So then let's see what happens here. So if we do this Zi minus G minus HK, okay, so this is your closed loop. This is the closed loop characteristic equation. Same thing. Because of the nature of the G here, there's lots of zero elements. Okay, most of them are on the off diagonal here. You plug the capital K over here times H, and then calculate the determinant of this. This one turned out to be Z to the power of n plus a1 plus k1 minus 1 here. Okay, so you get, so this will give us a closed loop characteristic equation, okay, for any k, for any case, this is general, basically closed loop characteristic equation here. Okay. Yeah. So now think back about the desired one, right? So this is basically the actual closed loop. This is the actual characteristic equation. And if somehow you have the desired one, so if the desired is Z to the power of n, let's call this desired one alpha C here. If desired is Z to the power of n plus alpha 1 alpha n minus 1 and alpha n. Okay. So let's say this is your desired closed loop characteristic equation. And where this desired from? It can be from a combination of different given pole positions, right? The locations of the poles. So essentially those are knowns here. Okay, so the alpha here. So now you see this is desired, this is actual here. Then you need the actual to be the same as the desired, isn't it? Right? Yeah. So now you can see you need a coefficient. You need the coefficients to be the same. So that actually is quite easy now. You need this coefficient to be this coefficient to be this, that coefficient to be this. So that gives us a very quick solution for the gain matrix element. So that gives us basically the K1 equal to alpha 1 minus A1, and up to, let's say, Kn minus 1 equal to alpha A minus 1 minus An minus 1, Kn equal to alpha n minus An. So see, this is the advantage if you have your the state space model, the system matrix G, written in the control canonical format. Right? If this G is written in the control canonical format, and that makes this solution for the K to be very simple. You can simply use the coefficient for the desired polynomial minus the coefficient for the denominator, right, in the original pulse transfer function, and you get your basic control gains at here. Okay, yeah. So that's the advantage for G to be in the control canonical format. But of course, the question here is not necessarily that matrix G is always written in the control canonical format, right? So the question basically is, so what if this G matrix, right, is not in the so-called control canonical form, right? And that's very common because many examples that we see that, especially when you pick a position, velocity for second order, that end results is not a control canonical form. Okay. Yeah. So what do we do in this particular case? If G is not in the control canonical form, what can we do? Transform. Exactly. Yeah. Excellent. We learned similarity transformation, right? We can always use similarity transformation to transform this G, the current G, into the control canonical form. So basically the solution is to transform the G, right, into control canonical. Okay, if that's the case. So if you recall in the lecture for similarity transformation, all you need to do is you need to basically come up with, coming up with, let's say, a matrix T. Then you use T inverse times T, okay? Appropriate T matrix, T inverse T, so the end results will be a control canonical. Okay, that's the idea. Okay. Now, the only catch is, right, what will be this T matrix? Okay, what type of T matrix will give us this desired transformation at here? So I'll give you the results at here without where the T is a proof at here, but you can take a look at the lecture notes or textbook for proof at here. So the T at here, okay, will be given by a multiplication of two matrices, M times W, and M at here, okay, is this matrix. Okay, so this is the M matrix. Can anybody tell me what the M matrix here actually is? Controllability matrix, right? Yeah. So W at here, okay, is this matrix. an minus 1 here, an minus 2 here, and up to a1. That's the first row. Second row, okay, which is this. So you can literally write down the rest of those rows at here. Up to here is a1, and then 1 at here, 0, 0, and then last row is 1 here, 0 here, 0, 0. That's W matrix. So if you construct the T matrix by multiplying M and W like this, then that T matrix will be the similarity transformation matrix. Multiplying T inverse GT will give us this control canonical format. Okay, yeah. So that's the idea if G is not in the control canonical form. Okay, yeah. Is that good? That's the first method. This is purely mathematics, linear algebra here. Okay. So let's talk about the second method. Okay, for obtaining the gain matrix K. Okay, so think of the second method here. This second one here is actually the most useful one, in terms of your hand calculations. Okay, yeah. So this one here, it's called second method here. You can just call this, which we call it Ackermann formula. Okay. So second one here is basically the so-called Ackermann's formula. So there is a very lengthy proof for this Ackermann's formula. You can take a look at the textbook for proof. Okay, I'll give you the results here for the proof. You can take a look at the page 409. Okay, there are a couple pages of proof for this Ackermann's formula. It's in our textbook. Okay, yeah. So what's the Ackermann's formula here? Okay, start with, let's say, given desired poles at here. So suppose they are lambda 1 and up to lambda n at here. Okay. So with the desired poles, we can obtain our desired characteristic equation of polynomial. Right? I think I listed it at the beginning of the lecture, so we call it alpha C Z. Okay. And that's basically, let's just rewrite it a little bit here. That's basically the characteristic equation of the closed loop system. Okay. That's given, right? You have the desired pole location, then you will have the desired characteristic equation at here. Okay. So Ackermann formula essentially has the following format. Here's Ackermann formula. The gain matrix K, okay, is equal to 0, 0, 0, 1. That's a column vector at here, times the H, GH, GA minus 1H inverse. So that's the inverse of the controllability matrix. And then multiply by alpha C G. There, that's Ackermann's formula. That's Ackermann's formula. The first two matrices, they're fairly straightforward. So the last one here is alpha C bracket G. So what that means is basically is, here's your desired characteristic equation, right? So all you need to do is replace that Z with G. So here you get G to the power of N plus alpha 1, G to the power of N minus 1 then plus alpha n minus 1g and alpha n. So that's the polynomial for alpha c of g. G is a matrix. Alpha 1 to alpha n, they're singular constant. So when you put things together, you get basically this is another matrix at here, right? So that's Ackermann formula. It's very elegant formula. It's easy to use. Okay, for G, it doesn't really matter what format it is. You can just always plug in, and you get your gain matrix K, right? Okay. So I'll give you an example. Okay, actually, you don't really need an example. This is so straightforward. So let me see. Maybe I have an example here. Otherwise, we don't have to. Yeah. This one here? Yes. Yes, you need to. Good point. Yeah. Actually, I don't need to show you any examples here. Now, in MATLAB, okay, you have a command basically called ACKER, okay, and that command, what you do is you feed in the G and H matrix, and also give a vector P. Okay, so vector P here. And that will return this gain matrix P. So P at here is a vector containing the desired pose. Okay, containing the desired pose. Yeah, I think it's quantum vector. So basically, let's say your desired pose is at negative 0.5, negative 0.2. Then the P is basically you can give say okay negative 0.5, negative 0.3. Right, that's your desired pose location, and then the K will be the feedback gain matrix. Okay.
How is ENGR different from place?
Very good point. So I was just about so there's another command called place. Okay. Yeah. Last time I checked, there is a very subtle difference. The place command. Okay. Typically, you use a place on. Place works for both SISO and the MIMO system, multi-input, multi-output system. Okay, so Ackermann formula. Okay, so this one here. Okay, this one here, works for MIMO. So Ackermann formula, unless the MATLAB has improved, used to be only for the single input, single output system. Yeah. Okay. Okay, so you have I think we'll have an example later combining with another one here. We'll use the Ackermann formula to calculate the gain here, okay? Yeah, we'll later look at an example later. So that's basically all about the pole placement, which is right now, which is the focus is on the regulation, right? Basically given initial condition and what is the system response, trying to bring it back to zero. Okay, so far it's about regulation, and but in terms of control, one very important aspect of the control is reference control, right? So let's take a look at the next topic. So let's look at control system design when you have a reference control problem. So sometimes this can be called tracking problem, right? You give a set of a reference input. Okay, it could be as simple as a unit step input, or it could be sinusoidal, or it could be a very sophisticated trajectory. Okay, but you want your system output to follow the reference input, right? That's reference control, and that's a tracking problem. Okay, so for state space design, okay. And when it comes to the reference control, the structure of the control loop looks like this. Okay. First of all, here's the plant. I'm assuming my plant is given in a state space model. Okay, so plant in state space model. Okay. So if it's a state space model, then you would be able to basically extract, okay, your state vector x of k, okay, out of here, and we'll give this state vector to our gain matrix k. Right. So up to here, this is basically the same as the regulation problem. You design your gain matrix k, right, and then multiply by the x of k here. But the difference is now we have reference input. Okay, so now we have a reference input now, and you have a junction at here, so negative feedback. Okay. So the reference input here, we're gonna insert, okay, a scaling block. Let's call it k naught at here, and then the two signals that are here adding together will be the control signal u, and of course here is your output y of k at here. Okay. So that's the simple structure for a reference control at here. The difference is you have a reference input, and then we have an additional block we call a scaling block at here. Okay, so I'll show you how to find these two blocks basically. Okay. So plant is the same plant, and that's the state space model that we have used. Here's your plant. Okay, here's a plant. And output equation. Okay, so no change, right? So this is the original system basically. But oops, where did that go? But the control is different now. So you see your control input u of 0, u of k, instead of just equal to negative k times x of k, you have a k naught times the reference input r of k here. Right. This is a different control input, right, compared to the regulation problem. Regulation problem, you don't have the k naught times r. Okay. And here you have a additional k naught times r of k. Okay. In terms of definition at here, see this k at here, right? This is no different. This is basically the gain matrix, the feedback gain. Okay, this is the feedback gain matrix. Okay. To find this feedback gain matrix, we can use exactly the same approach that we have just learned, right? So you can find this feedback gain matrix based on desired closed loop pose. Okay, so you can find this k based on the desired feedback pose. Use the Ackermann formula, use the place command formula, so you get your basically capital K, right? Yeah. So the question here is the k naught. How do we decide this k naught at here, right? So the k naught, okay, is called a scaling factor. Now this one here, okay, so I'll show you. This one here will be based on the so-called DC gain equal to 1. Okay, so this one you will find it based on the fact that DC gain needs to be 1. So now drop your mind. What does DC gain equal to 1 mean? Reference equal to output. Exactly, right? So you want the steady state error to be 0, right? That's what DC gain equal to 1 means. So here's a reference input. Here's the output. So basically you want the output to follow the input here, right? All you want here is your pulse transfer function between the output and the input, which is basically the closed loop pulse transfer function at here. So you want the DC gain of this one to be 1, so that'll guarantee that the output will follow this input at here. Okay, that's basically what it means. So so let's say this one equal to something, right? Yeah. So I'll use an example here to show you basically how to find a K and how to find a K naught based on the DC gain equal to 1 and here. Okay. Yeah. So let's go through an example here. Okay, given a system matrix G and H and output, okay, very simple system, simple matrix system here, and I want to design a closed loop feedback reference control system. So basically means I want to figure out this K and want to figure out this K naught at here. Okay, yeah. And the system here actually is good. Tells you I want to place the desired poles at Z1 and 2 equal to 0.5 plus minus J0.5. Okay, so here's our desired pole location. Now in the next lab, maybe not today, but maybe today a little bit. Yeah, so we will be able to actually identify. Let's say here's the desired pole, right? Then the question here is, okay, so what type of a system response does this desired pole give us? Okay, so system response basically means how much of overshoot, how much of a damping ratio, how much of time constant roughly this desired pole will give us, right? Yeah, that's what we're going to learn next here. Okay, yeah, is that a good location or not, basically? Okay. Okay, so given this one here, okay, here's the first step here. Okay, your first step should be always to check the controllability. Okay, because you're designing a controller, you're going to do the pole placement. So check the controllability, whether it's controllable or not. It's a necessary step. Okay, you have a controllability matrix. Just plug it in and see if the rank is full. Then you know whether it's controllable. Okay, so in this case, you'll see it's controllable for sure. Okay, yeah. And then second step is basically we derive the desired characteristic equation, because I'm going to use Ackermann formula to calculate the gain matrix. Okay. Desired characteristic equation, our symbol, we call it alpha C of Z. And that's the general format, okay, with a certain gain matrix K. And in this particular case, we're good. We have our desired pole location. There are only two here. So the first one is Z minus Z1. Second one is Z minus Z2. And what's Z1? Z1 is 0.5 plus J0.5. So that's minus 0.5 minus J0.5. Second one is Z minus 0.5 plus J 0.5. Desired pole locations. Okay, there are two of them. They plug in here, expand the two factors. We have our desired polynomial. Okay, so Z squared minus Z plus 0.5, and that's basically in the format as we alpha 1 Z plus alpha 2, right? Like that kind of coefficients here. Okay. This is not necessary. As long as you get to here, you know what the alpha C of Z is, then that's okay. So then step 3, step 2, step 3. Okay, so we can calculate this gain matrix K using Ackermann formula here. Ackermann formula. This is part of formula you can include in your final. This is the final material. Okay, and our system is order 2, so 0, 1, and then H, GH inverse times alpha CG. Alpha CG. Okay, so I will do probably I won't do everything. So what's alpha CG here? Alpha CG is, here's your alpha here, right? So it's a G squared minus G times 0.5 and then times that some unity matrix pi. That's alpha CG. Yeah. So G matrix is given, right? G matrix is given eventually, which is this one here. So use your calculator, use a hand calculation. In this case is fine. So 2 times itself minus G plus 0.5, and that gives us 0.34, negative 2, 0.32, 2.34. Okay. Yeah, seems about right. Okay. All right, so that'll give us this matrix here, alpha CG, right? And then you need to plug in this formula here. So another tricky part is the GH. So H is given, which is 0, 1. So here's 0, 1 here. Then G times H. So that's also pretty straightforward. So G times H. So this row times this column, this row times this column, and that gives us what? 1, negative 1. Okay. Yeah. So now you're putting things together. So inverse this matrix times alpha CG and then times 0, 1, and you'll get your K matrix, right? So that'll give us a K matrix if you calculate carefully. Okay. 0.34, negative 2. So the requirements for you guys, during exam, you have to probably calculate this use your hand, use your calculator. Okay, but when you do projects, you can always use command Ackermann formula, the ACK, to help you come up with the K matrix. Okay, yeah. Good. So that's our K matrix at here, right? So now step 4 now. Okay. So we have one more parameter to find, which is the K naught, right? So we need to find the K naught. Okay. So K naught here, as I said, is based on the fact that DC gain needs to be 1, right? So how do we find so for this part here, okay, let's say we're finding the K naught. Okay, finding K naught. To find a K naught, what we need to do is we need to derive the pulse transfer function between y of z and r of z. Okay, so we need to derive this one here. Okay, yeah. So this is basically the closed loop pulse transfer function, right? So where is that from? And that basically is from our original system, feedback system here. So this is your system, and then the U is the feedback, so we need to plug in the U back over here, and then somehow at the end derive a pulse transfer function between Y and R here, right? Yeah. So here's the simple steps. You'll see how it works. Here's your x of k plus 1. Okay, after you plug in the feedback U, so we get g minus hk, x of k, and then plus h, k naught, r of k. Okay. That's after plugging it here. Here's our closed loop system here, and then y of k is equal to c x of k, right? Yeah. So I'll temporarily call this one here g hat, and then I'll temporarily call this is h hat, right? It's h hat. Okay. So that essentially is like a similar format. This basically become x of k equal to g hat x plus h hat r, right? And the original system is what? Original system is x k equal to g times x plus k h times u, isn't it, right? Yeah. So it's basically like a similar format here now. So your pulse transfer function, what you can do, you can start from here. You can take a z transform both sides of this equation and z transform both sides of this equation. Okay. Group similar terms and derive a direct relationship between the y and r here. Okay. So your y of z and over your r of z, okay, which is called c times zi minus g hat, then times inverse times h hat. Okay, h hat. Yeah. So this is essentially the same formula, same kind of formula when you have a state space model. How do you reverse back to the pulse transfer function, right? Yeah, same thing basically. Okay. So this is your pulse transfer function, and you can calculate g hat, and g hat is g minus hk. Okay. K is already calculated over here, and that calculation will give us 0, negative 0.5, 1, 1. So that's your g hat, and h hat is h times k naught is 0, and k naught at here. K naught we don't know that, and we wanted to find out. Okay, so the next step is another step. You need to be very careful because you're gonna use zi minus the g and then do the inverse, right? It's a 2 by 2 matrix, and then you invert it. Okay. And with this inversion in here, you'll get you get a pulse transfer function for the y and r, which is this one. Okay. So that's the pulse transfer function. Okay. Yeah. And DC gain, if you recall, okay, the definition of DC gain of the system. Okay. Definition DC gain is basically, here is the pulse transfer function, and all you need to do is set the z to be 1. Okay, set it to be 1 here, and that gives us k naught divided by 0.5. Right. K naught divided by 0.5, and this DC gain needs to be 1. So set it equal to be 1. So set this DC gain to be 1. Then k naught can be easily solved 0.5. Okay, so 0.5. And I have a MATLAB, but somehow I didn't bring it here. I'll upload to the Connect. So they basically, I want you to check out the Simulink here. So check out on the Connect. I'll upload it later. Okay. Check out the Simulink file. Okay, on this example. And you can feel free to change the gain. If you change the gain, then you won't get basically you won't get a zero steady state error here, right? But if you choose these gains, the calculated gains that are here, then you will be able to get desired basically system response. Okay, so I'm going to upload this later. Okay. Okay, any questions so far? Okay, good. So before we move on here, there's one one more things I want to talk about. So this is a good time to talk about this. This is actually another different type of controller, okay, in this category. It's called deadbeat controller. Okay, yeah. Got deadbeat response. You don't find the deadbeat response in continuous system. You can only find the deadbeat type of response in discrete system, basically. Okay, yeah. So first of all, let's explain what does deadbeat response means here. Okay. So I'll skip myself. I'm actually not going to skip. So here is the system here. And then u equal to negative kx, right? Yeah. So if I substitute u back over here, so we get what? X of k plus 1 equal to g minus hk, then times x of k, right? Yeah. And then from here, you can iteratively try to solve for a solution. So I think I showed you already. So a solution at here is x of k equal to g minus hk to the power of k x of 0. Right? Here's a solution, basically. Solution for x of k. Right? That's a regulation problem, right? Regulation problem. Right. So this solution actually tells us a lot of information. Very simple solution. It tells us important information. Basically, you want to bring this x of k back to 0 from initial value x of 0. Okay. And how do you want to bring it back to 0? It's completely up to this g minus hk at here, right? It's completely up to this g minus hk. Okay. So here's a statement. Okay, here's a statement, and you can check out the page 415 for more rigorous and a detailed statement. And what I've put it here, okay, is more of a very simple statement here. So this statement, what it says is, okay, it is possible, okay, it's definitely possible to do what? To get this so-called deadbeat response And by deadbeat response basically means we can let our x of k, okay, to become 0 for how many steps? For the k greater than a certain q, and this q is less than n at here, and n is the order of the system. Okay, n is the order of the system. So let's say, for example, if n is, I haven't finished yet, for this one here, by choosing all the poles to be 0, okay, to be 0. Okay, that's a statement for deadbeat response. So if you look at this statement here, essentially, let's think about the real case at here, right? So let's say you have a system order 2, so you have a system matrix basically 2 by 2, right? Yeah. And if that's the system you have, and we assign the poles, there basically will be 2 desired poles, right? We assign both poles at origin, which is 0. Then I can bring this x of k back to 0 for how many steps? For at maximum what? 2, right? So within 2 steps, it'll bring it back to 0 basically. Yeah. That's essentially what deadbeat response means. Okay. 2 steps in this case means 1 sampling time, 2 sampling time. That's it. Okay. That's basically what it means. Okay. And it makes sense, right? You think about it. Forget about this deadbeat concept, but just think about the location of the poles here. Where is the location of poles? It's 0, isn't it? Right? It's 0. And when you have certain poles to the power of k, that's the response, right? The smaller the p is, the what? The faster this one will reduce back to 0, right? Yeah. So basically, the closer the poles to the origin or to 0 in the z-plane, then you would expect the faster response, essentially. Does that make sense? Right. So and then dead beat basically means, let's do the extreme. Let's put everything onto the origin there, right, to have a dead beat. It doesn't have a catch, though, right? So I'll point it out. But that's the nature of dead beat here, okay? Yeah.
Is it such a fast reaction time that it bounces all over the place for settles?
It will increase the control burden. Yeah. So you want it to behave faster, then you have to put in a low control effort or control voltage or current, right? So for certain combination, for certain cases, your control will become unbearable. Basically, will be beyond the capacity of the motor, essentially. Yeah. So I think I have. I think I have an example. Let me quickly show you there. Okay. Yeah. Okay. So I'm going to show you an example here. Okay. Yeah. But before we do that, let's summarize a little bit here. So basically, in less than n steps, your x of k go back to 0. Okay, and this is done by having all of the poles at 0 location. So that basically means the characteristic equation for the closed loop system become as simple as just z to the power of n, right? Yeah, it's a polynomial. Yeah. If you have a second order system, then you just z to the power 2. Okay. Yeah. All right. So let's illustrate this dead beat response through an example right here. Okay. Yeah. I'll use that double integrator for this example. Okay, so in this one we can see we want to design a dead beat response control for a double integrator 1 over s squared. Okay, and I think in the previous lecture I used a pole placement on double integrator 1 over s squared. Right? Yeah. So think about the process. I'll skip myself of some steps. Basically, how do you discretize this 1 over s squared and to obtain the discrete state space model? Okay, yeah, that part of things. Okay. So basically, in that example, okay, and we wanted to come up with this gain matrix K1, K2. Okay. So let's just give me a second here. The K1, K2, you mean? No. Yeah. Having the poles at 0 doesn't mean that K1, K2 will be 0.
Negative A.
Negative A?
Yeah, it's an alpha minus A.
Oh yeah. If your G matrix is written in the control canonical format, right? Okay. Yeah. But I'll show you. I wanted to bring back to that example here. Yeah. But unfortunately, that in that example, our G matrix, okay, was not written in the control canonical format. Okay. So this is double integrator, right? So with discretization, we end up with a G, which is this one here. Okay. That's your G matrix, right? This is not control canonical, okay? And this is based on the selection first state of position and second state is the velocity, right? Yeah. And then we design our K at here. If you recall, in that lecture here, basically we didn't really specify the pole location. We just specified the desired characteristic equation. Okay. Here's a desired characteristic equation. and end up with the gains that are here, okay, to be related to the desired polynomial P1, P2 coefficient like this, right? Yeah. So desired is z squared plus P1z plus P2. Okay. So this is the desired, right? Now, what would be the desired if we want to design a deadbeat response? The P1, P2 needs to be what? 0, right? So basically now the desired is z squared, basically, right? Just z squared here. So P1, P2 is 0. So that gives us K1 and the K2 value here. Okay? Yeah. So that gives us K1, which is 1 over t squared, and the K2 equal to 3 over 2t. So that's basically answer your question, right? You let the desired pole to be at the 0 location, and the gains are not 0, right? Yeah. That's your capital K at here, your gain matrix at here. Okay. So that's in terms of design. You basically you can stop here. So that's it. That's basically what give us a deadbeat response. Okay. Yeah. But we wanted to look a little bit deeper into this one here, especially with a different choice of this sampling time t. Okay. And what exactly type of effect, okay, does that have on the system response? Okay. So we'll look at different t values. So 2 seconds, 1 second, and 0.5 seconds here. So we'll look at the system response for this different type of things. Okay. 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 So here's what you can do, right? So it's basically what we're gonna do is here's a k here, right? So capital K equal to K1 and K2, okay, and which is of course 1 over t squared, 3 over 2t. Okay. So I'm gonna bring this capital K into the feedback of the system. That gives us the closed loop system, which is G minus HK times X of K, right? That's a closed loop system. And G, we have it here, H we have it here, and then the K we have it over here. Okay? So we get everything in here, right? So plugging this, all of the information here, you get this 1/2 of it here, 1/4 t here, negative t over here, negative 1/2 over here. Okay, and X of K. There. That's a closed loop system, right? That's a closed loop system. Okay. Okay, so let's verify the system response. Okay, let's verify. Here's what we're gonna do. Okay, suppose that my initial condition is 1, 1, right? Is 1, 1. So what do we want to do? We want to bring this initial from the system response from initial condition back to 0 in at most what? 2 steps, right? Yeah. So let's take a look at this here. I'll use basically. Let's use this t equal to 1, okay, for simplicity. Let's use t equal to 1 for illustration. Okay. So what is x1 at the first step? X1 here. So that equal to this matrix times x of 0, right? This matrix times x of 0, and that's 1/2, 1/4, negative 1, negative 1/2 times 1, 1. And that gives us 0.75, negative 0.5. Okay, yeah. So that doesn't seem to be very convincing, right? So let's take a look at the second step now, x of 2. And x of 2 is the same matrix out here. So 1/4, 1/2, 1/4, negative 1, 1/2 times this x of 1, right? So times 0.75, negative 0.5. And if you do this right here, then you'll get 0, 0. Okay? Yeah. So basically, if you plot response for x1 and x2 of k, so x1 starts from 1.75 back to 0, right? and the other one is 1, negative 0.1, negative 1.5, and then back to 0. Okay, yeah. The second one seems to be actually pretty jumpy, you know, from positive to negative, and then back to 0, right? Yeah. So that's actually one of the things about this deadbeat response here. And you can keep going. You can basically, if you can see if it's whether it's being maintained at a 0 or not, right? If you keep going, you get the rest of them will be 0 too. Okay, yeah. Now, and the other thing is what we also want to check is the control signal U of k. Okay, so we also want to look at how much control effort there we're putting into it. Okay, we're putting into it at here. Okay, yeah. So we have our U of k equal to negative k times x of k, right? We have our control effort at here, all right? So I can calculate, okay, so U of 0, right? For U of 0, what is that equal to? Where's my k? My k is over here, right? This is the k, so 1 over t squared, 3 over 2t. And then times x of 0. X of 0 is what? It's 1, 1, right? It's 1, 1. Okay? Yeah. And that gives us negative 1 over t squared minus 2 over 3t. Okay, so we're really looking into the details, right? And what about, let's say, the second moment at here, right? This is basically u of 1 at here. Okay, u of 1, same thing, x negative k times x of 1. Okay, so that gives us how much? If you plug into the x of 1 here, this is x of 1 here, right? So you should get 1 over t squared and plus 1 over 2t. Yeah, in this case here, I'm more of using a general expression here. So let's think about the particular case. So if I have t equal to 1 second, and I got my u of 0, t equal to 1 second plugging here, I got a t equal to u of 0 equal to negative 2.5, and u of 1, which is basically this 1.5 at here. Okay, yeah. So if you try a smaller sampling time, let's say 0.1 seconds or 0.5 seconds, actually should let's use 0.1 second. So then the u of 0 you'll find is this is becoming, because this is 1 divided by t squared, right? So this u of 0 become negative 115, and then the next one here, this is u of 1 that become 105 here. Okay, yeah. So what this number tells you is, especially this one here, your first control input is negative 115, and then the next moment it becomes positive 105, right? Yeah, that's a dramatic change. You know, you have a very fast switch. Not only a fast switch, but also you have a huge magnitude jump at here. Okay, yeah. And if this is in volts, then I don't think you have that much voltage input to the motor, right? Yeah. So that's basically the catch in terms of the deadbeat response. Okay, yeah. There's no situation that can really be so ideal. You know, there's always a catch, basically. Okay. Okay. So in the lecture notes, check out this MATLAB simulations here. Okay. Yes. Oh, the sampling. You mean this sampling time here? A lot of time experience. Yeah. You know, typically for robotic system, you need a fast response. Okay. 0.01, 0.001. It's a typical sampling time. Yeah. Yeah, that's right. That's why you know, you don't want to you don't want to design a deadbeat response. You have to keep this in mind, basically, right? Yeah. So, but deadbeat response is a type of response, right? It's a type of controller design, basically. Yeah.
I have a question for
yeah.
the gain K. In this example, you define the first element as being K1. Previously in the
You mean here?
in this lecture,
Yeah.
you started out with Kn, so the higher order K is the first element in the matrix. So is there a specific convention that everyone was supposed to use, or
You mean at the beginning of this lecture or previous lecture?
this lecture?
Oh, this lecture. What did I do this lecture? Like this? Sorry, I didn't quite get your question here.
Yeah. Keep going down. Where you have K.
Where?
Up a little bit.
Up a little bit?
Right there.
Yeah.
Kn and Kn minus 1.
Right.
So it's in decreasing.
Oh, you mean the subscript? Oh, that really doesn't matter. Yeah. That's just the notation-wise. Yeah. Oh, you're right. I guess here, what did I use here? K2, K1, K.
But that's because you're using the previous lecture, and that's how you defined it. You just
Yeah.
switched the way you defined it in those lectures.
Yeah, you're right. Actually, just want to double check. That's a really good point. In the example here, did I use K1, K2? Yeah, that's right. Yeah. But it really doesn't matter. That's just notation. Yeah. Okay, good. All right, so still have a few minutes here. Any questions? Yeah? Okay. So now let me start the next lecture just a little bit here. And now I'm going to have to temporarily stay away from the state space domain, okay, state space equation. Okay, we'll come back. And we'll move back to the z-plane, okay, S-plane, z-plane, and then also the pulse trans function a little bit here, okay? So what we really want to cover is actually the idea of in the pole placement we have asked ourselves, why do we place the pole at that location, right? What exactly does that pole location means to us, okay? Or in other words, what type of response does that pole location will actually give us, right? That's the answer we want to figure out. And to figure out this one here, what we need is, we wanted this part of the lecture here is basically, we are looking at this mapping from S-plane to Z-plane. Okay, mapping from S-plane to Z-plane. So what is that? First of all, before we talk about mapping from S-plane to Z-plane, I guess one thing, I need a picture from a previous lecture. Okay, so let's bring this one here into today's lecture. And you have learned control system mostly in the continuous domain, right? When you learn the control system in continuous domain, one of the things is basically what you learn is basically what exactly is the pole location in the S-plane corresponding to in terms of system response, right? Yeah. So here's the graph. I think you've probably seen it. I don't know if you remember. So this is S-plane and here. If you have a pole in S-plane, for example, somewhere here, right? This is on the real axis, which is on the left side of the S-plane, right? Then for that particular pole, it'll yield a system response which is more or less exponentially decayed type of response. Okay? Yeah. So what this one really means is, for example, you're given a system transfer function. It's a very rough example. Maybe, okay, it consists of a number of, okay, poles at here. So this S1, let's say this is S1 in here, right? This S1. So you can do a partial fraction expansion on this one here. You get this basically S plus S1 here, and then S plus S2, right, like this, okay? Yeah. And then you do an inverse Laplace transform, And for this particular one here, you get e to the power of basically negative s1t, right? Yeah. So if this is s1 over here, so this is basically exponentially decay, right? That's the response. If your response, okay, s1 or s2 is somewhere over here, okay, that's basically means it's a complex root, okay, and typically there will be another one, the pair one over here, right? Yeah. And of course, I shouldn't write it, because if it's a complex, then it's not going to be as simple as this. It's going to be a second order over here, right? Second order. Then the response, right, will be oscillations, but it has an envelope, right? You'll have an envelope of exponential decay there. Okay, yeah. And if this pulse is right on the imaginary axis, okay, imaginary axis here, then you would experience basically a constant oscillation. Okay, that's basically what we call critically damped. Is it critical? Yeah, right. Critical damped situation here, right? Yeah. So if the pulse is on the right side here, right? So it either exponentially increase or oscillating and exponentially increase, right? Yeah. So that's basically the pre-knowledge that we learned for continuous system, and what will be the system response for different locations of the pulse in the S-plane, right? That's what we learned. Okay. So the objectivity here is, okay, see the objectivity here, okay, is to establish, okay, we want to establish a similar, okay, mapping, okay, in the Z-plane. So in the Z-plane basically means you have a unit circle right here, okay, and we want to know, okay, what each one of the locations inside the unit circle or even outside the unit circle, what type of response will the system behave or give us with respect to the location of that pulse over there. So that's what we want to establish, a similar mapping in the Z-plane based on, okay, S-plane knowledge. So we're not going to do it from scratch. So we will try to make use of this knowledge from in the S-plane as much as possible to establish the similar mapping in the Z-plane. So that's the objective here. Okay, that's the objective. So I'll give you a very simple example. Okay, and if you recall that in probably the second lecture. Okay, in the second lecture. In the second lecture, what we did is we said, okay, here is a continuous signal input, right? Continuous signal input, and let it pass through. Okay, let it pass through a impulse sampler. Okay, so you establish basically, okay, a sequence of impulse outputs at here. That's a sampling process, right? That's a sampling process, and we call this is x of s. This is x star of s, if you recall that, right? Yeah. And then from x star of s, we'll be able to get what? X of z, right? And how do you transform from x star to x of z? X of z. What do? You replace the s with what? 1 over t ln z, right? Yeah. Or, which is what? Z equal to e to the power of Ts. Okay, it's part Ts. So that's the connection between the Z and the S here. So this one basically establish a mapping from the S to the Z. Okay, to the Z. So one simple example, and then we'll call it a day here. So for example, right? So I'll call this is case number 1. We'll continue. So let's say we have a very simple system in S-plane. Okay, in the continuous domain, 1 over S plus B. And this 1 over s plus b corresponding to exponential decay function e to the power negative bt. And you can sample this signal at here. What do you get? You get a negative bkt, right? Capital T, sampling time, right? Sampled it, you get this. Okay. And then this one here, you can write it negative bt to the power of k. So that's a sequence of numbers, right? Sequence of numbers. Okay. Then you can do a z transform of this. You get a z over z minus e to the power negative bt, right? So you see, originally s is negative b. Where is the new location of the poles now? Is z equal to e to the power of bt, okay? Negative bt, yeah, negative bt, right? So that's basically the formula, z equal to e to the power of ts, okay? Yeah, that's just one simple case. I'll show you a couple other cases here, and then we'll try to establish our rules in terms of mapping from S to the Z plane, and also establish the similar system response in the Z plane. Okay. So I'll see you on Thursday. Okay. So no lecture. We'll have the midterm exam, okay? And make sure you come here a little early. If there's no class in front of us, then we can start early too. Okay.